Evaluate the definite integral from 0 to pi by 2 cos square x upon cos square x plus 4 sin square x with respect to x. With reference to these various types, let's now try to integrate this new function. To prepare this function for a suitable substitution, I am going to divide by cos square x first. When I divide by cos square x, numerator becomes 1. Denominator 1 plus 4 tan square x. Sin square x by cos square x is tan square x. Here, it is simplified. But what's the use? If we go for a substitution tan x, u equal to tan x, its derivative should have been present here. Tan x derivative is sec square x, which is nowhere seen. Then how can we go for the substitution? So, I'll first create that sec square x here. Multiply and divide by a sec square x. But then the numerator derivative is okay. But this sec square x in the denominator becomes unnecessary. So we need to change that also. I'm changing it into 1 plus tan square x. That is a trigonometric identity. Sec square x is 1 plus tan square x. Now it's okay. Luckily, we are able to change the complete thing in terms of tan x function. Its derivative sec square x is already prepared. So we will go for the substitution. U equal to tan x. Then du is sec square x. So this function du upon 1 plus u square into 1 plus 4u square. But don't forget, it's a definite integral function question. These limits 0 and pi by 2 are for this variable x. But we are planning to change the variable to u. When x is 0, what will be the u? Let's see. When x is 0, u is tan 0. So u will also be 0. The lower limit will also be 0. But when x is pi by 2, the upper limit, then what about u? U will be tan pi by 2, which is infinity. So when you rewrite this function using this substitution, change the limit also to the new numbers 0 and pi infinity. Moreover, you watch. This is no more a trigonometric function. So these angles should not be the limits. Angles are now changed. Now how to integrate it? This is now a rational function, a polynomial in the denominator and a polynomial in the numerator. A polynomial in the denominator and numerator makes it a rational function. Rational functions are integrated using partial fraction method. Which partial fraction? In fact, the partial fraction to be applied is this. The second degree non-splittable factors corresponding to them, we need to take first degree polynomials in the numerator. That is what this method says, the third type. But observe here, the first degree terms are absent. No u here, no u here. Because of that, we can even go by a direct substitution, a and b. Why? If you still feel you want to calculate like this, in this method only, fine, no problem. Go ahead with that. What would happen is, the coefficient of x here a and coefficient of x here c, both will become 0. And ultimately you will be getting b upon x square plus 1 and d upon x square plus 4 for some constants b and d, which is what happening here. Then why to have the hassle of calculating 4 unknown values? We will go directly. So, I'm taking the LCM here. 1 plus u square into 1 plus 4u square LCM, which is the same denominator on the left side, cancel. So a into 1 plus 4u square plus b into 1 plus u square is the numerator, which will be equated to this one. Now, these two polynomials could be equal only if the coefficients of like terms are equal. U square here 4 times, u square here b times. So 4a and b. 4a plus b should be equal to the coefficient of u square on the LHS is 0. So 0 equal to 4a plus b. Now equating the constant term a and b. a plus b should be equal to 1 because the left side constant term is 1. Solving for a and b from these two equations, we get a is equal to minus 1 by 3 and b is equal to 4 by 3. Now we are in a position to change this integrand, this single one in this form with the help of newly calculated a and b. So, definite integral 0 to infinity minus 1 by 3 upon the first factor as we suggested, 4 by 3 upon 1 plus 4 u square, and using this a and b here. Alright. Now these are two terms to integrate. Let us separately write them with the coefficients out. Minus 1 by 3 here and 4 by 3 here coefficient. Also, 1 upon 1 plus u square, 1 upon 1 plus 4 u square. Both of them we are going to integrate using this pattern. 1 upon x square plus a square, the tan inverse formula. But remember, in that formula, the coefficients of x square should be 1. Here it is okay, coefficient of the second degree u square 1, no problem, direct formula. But what about this? This one had the u square coefficient 4. First of all, make it 1 by dividing by 4. When I divide by 4, I have to multiply also. That 4 in the denominator is balanced here. So, 1 by 4 plus u square. Or in other words, we can say taking u common out from here. Taking that 4 out, this 4 joins the 3 here and 1 by 4 here. So according to this formula, the integration is 1 by a tan inverse x by a. So here a is 1, here a is 1 by 2. Why 1 by 2? Because it is 1 by 2 whole square plus u square. So the integration is minus 1 by 3 tan inverse u by 1. Here a is 1. Here a is half. So 1 by a tan inverse u by a. 0 to infinity. Let's go ahead. We need to simplify by giving the upper limit and lower limit now. These coefficients are slightly adjusted. This half goes as 2 in the numerator. This division by half is 2u. Now let's apply the upper limit and lower limit in them. Here tan inverse infinity minus tan inverse 0 plus tan inverse 2 infinity minus tan inverse 2 into 0. What is tan inverse infinity? Pi by 2. Tan inverse 0, 0. Again tan inverse infinity, pi by 2 and tan inverse 0, 0. So we have, along with this minus 1 by 3 and 2 by 3 coefficients, we have this. So simplifying it further, we get the answer pi by 6. Found it useful? Don't forget to subscribe Marriott Joseph channel for variety of examples and various topics.